Sie haben als erster den Faktor quantentheoretisch abgeleitet, wenn auch wegen des Polarisationsfaktors 2 nicht ganz streng. Es ist ein schöner Fortschritt. Mit freundlichem Gruß, Ihr A. Einstein.
This is the place where I have spent my childhood and my formative years. This is where, as an adult, I spent hours with my dear friend Meghnad, poring over the works of Wien, Boltzmann, and of course, Max Planck. Meghnad translated for me the original German papers into English. The papers were about black body radiation.
Oh wait, let's turn this into a black body.
Wait, I also have something in my bag. How much you will try, it will never be a black body.
Little did I know at that time that radiations trapped in a black body would bring about a turning point in my life.
But the black body is the idealized concept that actually neither reflect nor transmit. Whatever the electromagnetic radiations incident upon it, it absorbs completely. That is the concept of a black body.
Now I'll show you a very simple black body. It's a box here in which there is a small hole. Then you can see that light goes through this hole. Now let me close this box. The hole is still there. Can you see any light coming out of it?
So you need a kind of a closed enclosure. Doesn't mean that inside has to be black. Any radiation trapped inside an enclosure where the temperature is uniform so that you're not allowing, energy flux or heat flux to come from outside or go from inside to outside. So that the system is what we call in thermal equilibrium, then it's a black body.
How do I determine the character of the radiation which is inside and which is in equilibrium at some temperature? Of course, I can raise the temperature of this body. So the characteristic of the radiation inside will keep changing.
You take an iron rod and you heat it. If you get little closer to it, you will feel some heat type of energy is coming from it. If you will increase the temperature more and more, after some points, you will see some dull red color. If you increase the temperature more, you will see some bright red color. If you'll heat more, it will be some white, and if you'll heat more, it will be blue.
Right from radio waves all the way up to gamma rays, you needed specially designed detectors which can detect that radiation. That took a long time.
Let's try to plot a graph which is here. This x-axis is the frequency and the y-axis is it's called radiancy. So experimentally, people observe that this curve is like this type. Okay. So that means at a constant temperature, this black body actually radiates all possible frequencies. But you see, for a particular range, these frequencies when your body, your black body actually emitting this frequency most likely. If you increase the temperatures, this graph will change. Then the most likely frequency would also shift towards these directions. And that's why this, when you increase the temperatures, the color of your body is changing. Some properties of this black body actually can be described by the Stephen's law. Another important law is the Wien's displacement law, that is saying that nu maximum is proportional to T. Stephen's law was given around 1879, and the Wien's displacement law is given around 1893.
I was born in the year 1894. Meghnad was born a few months before me. In our colonized nation, Western science had begun to take firm roots.
Both Bose and Saha were in MSc class together, and then they were appointed lecturer in physics by Sir Ashutosh Mukherjee, I think, the Vice Chancellor at that time in Calcutta University. And Saha would translate papers by Pauli and Einstein and explain them to Bose. And then eventually Bose, I think it was Dr. Hartog or somebody who was the Vice Chancellor of Dhaka University, he appointed him as reader. So he moved to Dhaka.
At Dhaka, I initially felt a little cut off. But they had given me an offer that I could not refuse.
Dhaka University had just been set up. So he started teaching a few subjects, which included quantum theory. Now, in those days, quantum theory is nowadays called old quantum theory. Quantum mechanics had not yet come. So let me call them all shots in the dark. The first shot was Planck. The second shot was Einstein, 1905, where he said light itself consists of a stream of particles. We call them photons. The third shot in the dark was in 1913, when Niels Bohr gave his atomic model. At that stage, the main problem in quantum theory was a proper theoretical deduction of what is called the Planck law, Planck's spectrum. And while teaching, he found it very difficult to explain to his students exactly what was happening, because there was no proper theory.
We need some complete theory of this energy density functions or this radiancy, which can actually completely experimentally fit this graph. But the expression is actually 8 pi nu square by c cube kt d nu. That is the following expression. Now, what will happen if you plot these things in the graph? Will it actually give you the same experimental curve what we have seen earlier? Let's see what happens. Earlier curve was this one. Now, if you plot this one, what will happen? It will go this way. It is not completely matching. In fact, for the low frequency it is matching, but for the higher frequency it is not matching. So it is called ultraviolet. So this is the range of ultraviolet range. In this ultraviolet range, this classical theory actually completely disagree with the experimental results. So this phenomena is called ultraviolet catastrophe. So this is the big question marks. Why our known classical theory, we are so fond of it, cannot explain this black body radiations. Then we come up to the year 1900, where Planck actually come up with some new hypothesis to explain this curve.
Before 1900, what was known are actually two limits of what we call the Planck distribution law. One is the high temperature limit. So when we say high temperature, we mean that the temperature is much larger than the energy of the light. And in that regime, it is called the Rayleigh-Jeans law. And Wien's law, where the energy density is proportional to nu cubed exponential minus some gamma, a factor, nu over t, where gamma is a constant. So this is at low temperature, high frequency. Now what Planck did, so this matched with experiments in the corresponding limits. What Planck did in 1900 was to actually match these two expressions. And what he got, therefore, a plot of E of nu versus nu at different temperatures. And so this curve roughly looks like this. So this is Wien, and this is Rayleigh-Jeans, okay? The low frequency and the high frequency behavior. And with temperature, the maximum would shift. So this is Planck in 1900.
I mean, he then finally came to the conclusion that the material of which the black body is made, the walls, they do not absorb and emit radiation continuously, but in discrete quanta. Okay, so this was a very bold hypothesis. He said it was an act of desperation. But even then, to get to the final step, he had to assume something or the other. So Planck's derivation was not a very satisfactory derivation. His formula was perfect. But to get to the formula from some theoretical basis, there were a lot of problems.
In the year 1900, I started going to school.
Then comes Einstein in 1905, the famous paper that we know as photoelectric effect.
The emission and absorption process is discrete. Light itself consists of a discrete set of energy packets. He called them light quanta. Today we call them photons. So the idea of photons was that of Einstein. Einstein's light quantum hypothesis was not accepted by many physicists in the West because there was an apparent contradiction between light being a stream of particles and light also showing interference effects, which is typical of waves. In fact, that gave birth to what is called wave-particle duality.
He assumes that the electromagnetic radiation is a gas, is an ideal gas of what he called light quanta. If there are n such light quanta in the room, in the black body, then the total entropy will be nth power of that volume. What he gets is a remarkable expression that if there are n such quanta, then the energy is n times h nu. So today we know it as the energy quantization formula, where n is the number of, we call them photons now, h is a Planck constant, and nu is a frequency. So this is the remarkable result. And from this, actually, he derived what the Planck constant should be. And then Millikan measured it 8 years later and got complete agreement with Einstein. That 1905 Einstein was like a karma yogi Einstein. Okay, he is deriving things which are matching with experiments. He's calculating the Avogadro number, the Planck constant, etc. 1905 is considered the miraculous year of physics because Einstein wrote 3 momentous papers. What are these papers on? One is a theory of the Brownian motion. which is an explanation some 80 years later of something that was observed by Robert Brown, an Irish medical practitioner whose hobby was to look at things with a microscope designed by himself. Similarly, then comes the other paper, which is known as photoelectric effect, but actually it was Einstein's analysis of the Planck radiation law, and the outcome was the photoelectric effect, which basically says that if you shine light on a metallic plate, then electrons get ejected. And so only in the case of special theory of relativity, Einstein did not have the benefit of many experiments, though Michaels and Morley were there. So he did some Gedanken experiment, thought experiments of what would happen if he were to travel up and down in a lift.
In 1905, Bengal was partitioned. We took to the streets in a protest march and tied Rakhis on our friends' wrists, both Hindus and Muslims.
What Einstein did in 1905 is really not a derivation. Einstein was putting pieces together of Rayleigh jeans, Wien, and then putting them in juxtaposition with the Boltzmann idea of thermodynamics, and then actually getting a value of the Planck constant, etc. Bose wanted to derive this. So Bose was struggling with that.
And while teaching, he found it very difficult to explain to his students exactly what was happening because there was no proper theory. And so he was grappling with these ideas.
Thereby, Natanson, Ehrenfest, and Planck himself were bringing in new perspectives. But there was still something amiss.
But what is very interesting for me is the complementarity of research with teaching. How by teaching a class, you get ideas of research. And this is a classic example because students were constantly asking, "Sir, how do you derive this Planck radiation law?"
So imagine a young teacher in Dhaka confronted with all these possibilities, trying to teach this to his students. He was very dissatisfied. And he found that the main problem with all these derivations is that Planck's law consists of two factors. The first factor is 8 pi nu square over c cube. The next factor is h nu divided by exponential h nu divided by kt minus 1. Now, it's the second part whose derivation all these people, the great physicists of the time, they were trying to give an explanation of that. But as far as the first factor is concerned, they took it from classical theory. Classical is a number of modes in a volume. This Professor Bose found very unsatisfactory, that you should use both classical physics and partly classical physics, partly quantum physics. So he said, no, I must give a derivation, completely quantum theoretic derivation of the whole formula. And that is where his genius was expressed. He gave a derivation.
What Bose did in 1924 was quite revolutionary. He showed us how to count what we call now fundamental particles. This was a new method altogether. And so what came out of it is a kind of a new statistics. While Einstein was looking at the macro physics of entropy, etc., thermodynamics, Bose wanted to go to the micro world and go and do how to do this counting.
He sent this paper to Philosophical magazine. They probably rejected it. Then he wrote a letter to Einstein.
Respected sir, I have ventured to send you the accompanying article for your perusal and opinion. I'm anxious to know what you think of it.
You will see that I have tried to deduce the coefficient 8 pi nu square by c cube in Planck's law independent of the classical electrodynamics, only assuming that the ultimate elementary region in the phase space has the content h cube.
I do not know sufficient German to translate the paper. If you think the paper worth publication, I shall be grateful if you arrange for its publication in Zeitschrift für Physik.
Bose's first contact with Einstein was when he and Meghnad Saha were translating Einstein's papers on relativity, which were written in German, into English. So he wrote asking for his permission. And Einstein, of course, gave them the permission, but I believe he put a clause that this should be only meant for buyers in India.
I do not know if you still remember that somebody from Calcutta had asked your permission to translate your papers on relativity in English. I was the one who translated your paper on generalized relativity. Yours faithfully, S.N. Bose.
And then he sent a kind of a manuscript. Interestingly, the details of the manuscript are not known. What was known is what Einstein communicated.
Einstein had assumed that photons travel like ordinary particles. They're all independent of each other. Then immediately, several scientists pointed out, but then you will never get Planck's law. Planck's law requires some other way of propagation. And this is exactly what came out of Professor Bose's work, that these photons are not like ordinary billiard balls. They are what's today, in today's language, called indistinguishable.
So consider about a 2 box labeled with 1 and 2, and consider the 2 distinguishable particles. Now, according to the Maxwell-Boltzmann statistics, what are the valid states? Now, if they are bosons, like they are not distinguishable, they are indistinguishable, then the valid states would be
He was the first one to give a complete theoretical derivation of the entire Planck formula, including the first factor. Now, in the first factor, what he showed was that it gives the number of possible states of a photon. Now, once you know, and that is fixed, now once you know the states, you can start distributing photons in them. If I interchange these 2 balls, will I get a new state, new arrangement? No. Why? For this to give rise to a new arrangement, I need to have another box. Let me put it here. And then these 2 balls, I can interchange and put there. So you will have one like this, another like that. So, but I need another box, but I don't have that. So by interchanging these 2, I don't get a new state. This is indistinguishability. And this is inevitable in the way Bose did it.
Einstein saw something deep in this.
Lieber Herr Kollege, ich habe Ihre Arbeit übersetzt und der Zeitschrift für Physik zum Druck übergeben.
But he commented that he was certainly the first person to give a proper quantum theoretic derivation to Planck's law, except that you introduced a factor of 2, not entirely logically. So Einstein then was so excited that finally his concept of photons was given a very strong theoretical justification. He went gaga. And he wrote 3 papers within 6-7 months. So he applied it to material atoms. And then he was absolutely stunned, because when he applied it to material particles, he found that material particles should have a wave nature. Now, he had himself proposed that something which had a wave nature, light, should have a particle nature, wave-particle duality. Here is a case when application of Bose's statistics to material atoms tells you material atoms should have waves, a wave character. So he was stunned, and he immediately remembered that some French fellow called Louis de Broglie had sent him a thesis about a year back, where he had also proposed that material particles, in analogy with Einstein's theory, that if photons have a wave character or where light has particle character, then something we know as particles should also have a wave character. Now, he did it by pure analogy. Einstein was not impressed. He put away the paper. But when he saw Bose's paper, that came back to him and said, what a great idea. It's not just an analogy. It is actually there because of statistics. So he wrote back to de Broglie's thesis supervisor, Paul Logement, and asked for a second copy, which he sent him. And then Einstein started writing these papers, explaining Bose's statistics, bringing in de Broglie's hypothesis that material particles should have a wave nature. And finally, he came to the conclusion that at very, very low temperatures, below a certain critical value, such Bose gases should condense into the lowest possible energy state, which nowadays called Bose Einstein condensates.
So then what Einstein did, he then calculates the pressure, and he finds that the pressure is lower for identical gas of bosons. I'm calling them bosons already because the name came later, than if these particles were distinguishable. And so that gave rise to the idea of a condensation, that so many bosons would flock together. Helium-4 will, at sufficiently low temperature, will then go into a condensate. And this is what we call today Bose-Einstein condensation, which was discovered experimentally many, many decades later.
And then, of course, later on, as we all know, the wave character of electrons were actually seen in an experiment which Davis and Germer had carried out. And then the question came, if material particles have a wave nature, what is the equation of that wave? And eventually that equation was written down by Schrödinger, and that gave birth to what we call today quantum mechanics. So you see how Bose's work stimulated the development of quantum mechanics.
Es ist ein schöner Fortschritt. Mit freundlichem Gruß, Ihr A. Einstein.
In October 1924, I set sail for Europe. I was on a 2-year study leave granted by University of Dhaka. In Paris, 17 Rue des Camarades was a favorite nest for Indian students, including the ones involved in the nationalist movement. Madame Curie graciously allowed me to work at her Radium Institute. But I had to brush up my French before she took me in. I also attended Paul Langevin's lectures and worked in Maurice Debray's X-ray crystallography lab. But my heart was set to meet Einstein in person.
The first paper he sent, as I already said, to Einstein, which Einstein immediately accepted and told the entire story. But within a very short time, perhaps about a couple of weeks, he also sent his second paper.
Dear Master, my heartfelt gratitude for taking the trouble of translating the paper yourself and publishing it. I just saw it in print before I left India. I have also sent you, about the middle of June, a second paper entitled Thermal Equilibrium in the Radiation Field in the Presence of Matter. I'm rather anxious to know your opinion of it, as I think it rather important. I shall wait for your decision as well as your opinion on my second paper here in Paris. Yours sincerely, S.N. Bose.
In the first paper, you will find something extremely striking. There is not a single reference. Whereas in the second paper, you will see references to all the previous work, which means he actually wanted these two papers as a kind of single paper in two parts. So the first paper was only about the intrinsic property of radiation in equilibrium. And he showed that Planck's formula follows not because light is getting emitted or absorbed by anything, by its own nature. Because of photons and their statistics, you get Planck's law. But in the second paper, he introduced matter. And again, he showed that it doesn't matter what the mechanism of emission and absorption is. You always get Planck's law. And then he showed that all the previous attempts by everybody followed as special cases of his most general formulation. This was the first part of the second paper. And Einstein translated it and published it.
Dear colleague, thank you sincerely for your letter of 26th October. I am glad that I shall have the opportunity soon of making your personal acquaintance. Your papers have already appeared some time ago. Unfortunately, the reprints have been sent to me instead of you.
But he had a second part, in which he considered a specific case, the Einstein case of two-level atoms where energy is absorbed and emitted. And Einstein had said the emission has to be of two kinds: induced emission and spontaneous emission. The spontaneous emission is the one which gives rise to Planck's law. Now, Bose showed that it's not, Bose's argument, general argument was that it's not necessary to split the emission process into two parts like this. Emission is emission. So, since everything follows from the new statistics, we should not separate these two. If we assume induced spontaneous emission, then from the formula you will see that there is an induced emission also, and also vice versa. He didn't show the vice versa case in this paper. Now, Einstein objected to this by putting this time an adverse note. He published the paper but put an adverse note that I do not agree with Bose in this particular respect. So he was very perturbed. Now, he held Einstein in great esteem, so he started thinking, what could be the problem? Why is Einstein objecting like that?
Revered Master, I received your kind note of 3rd November. I have been thinking about your objections all along, and so did not answer immediately. It seems there is a way out of this difficulty. I have written down my ideas in the form of a paper, which I send under a separate cover. It seems that the hypothesis of negative Einstellung stands, which reflects the classical behavior of a resonator in a fluctuating field. The views about the radiation field, which I have ventured to put forward, seem to be very much like what Bose had recently expressed in the May issue of Philosophical magazine. But it is only a guess, as I cannot say honestly that I have understood all he means to say about virtual fields and virtual oscillators.
So he wrote a third paper, which he also sent to Einstein, but Einstein never even responded to it. So these incidents actually dampened Bose's spirit quite a lot. Now, Bose went to Berlin in 1925 and met Einstein. They discussed all these problems.
In 1925, Einstein was the director of the Kaiser Wilhelm Institute. Berlin was exploding with groundbreaking discoveries, and Einstein was the center of gravity of all the debates and discourses around these discoveries. Dear Jacqueline, everybody seems to be quite excited in Berlin about the way things have been going on with physics. On the 20th last, Heisenberg spoke in the colloquium about his theory. Then, in the last colloquium, there was a long lecture on the recent hypothesis of the spinning electron. Perhaps you have heard about it. Everybody is quite bewildered, and there is going to be very soon a discussion of Schrödinger's papers. Einstein seems quite excited about it. The other day, coming from the colloquium, we found him jumping in the same compartment where we were, and forthwith he began to talk excitedly about the things we have just heard. He has to admit that it seems a tremendous thing, considering the lot of things which this new theory seem to correlate and explain. But he's very much troubled by the unreasonableness of it all. We were all silent, but he talked almost all the time, unconscious of the interest and wonder that is exciting in the minds of other passengers.
But Einstein was at that time working out his three papers based on Bose's work. It's quite strange that Bose was present there. He was a young man. He was not asked to collaborate. Now, why that happened, I do not want to speculate, but that is a fact. Although Bose was not asked to actually collaborate, there is some evidence that Einstein had asked him to calculate something, namely that by considering fluctuations of these particles in small volumes, what would be the nature of the fluctuations? And there is, we got a piece of paper from the Einstein archives written in Bose's hand, where you can clearly see that Bose had calculated the fluctuation, in which it shows two terms. One the wave-like term, the other the particle-like term. So the fact that Bose statistics gives rise to these two terms, Bose also knew. And that paper exists in the archives of Einstein.
I mean, Gamow wrote 30 years of physics that shook the world. And so this is the end of the 30 years. I mean, from 1920 onwards, I mean, of course, Niels Bohr was there in 1913, but 1920 onwards up till 1928, 1930, it culminated with the Dirac equation. There was a flurry of activity, but I don't think Satyendranath Bose continued to work on quantum mechanics per se in great depth or detail, but he had many other interests, as I said before.
Nobody has seen the third paper. Bose never kept a copy, Einstein didn't keep a copy, so we don't really know what was written, except that there is a letter from Bose to Einstein saying he has shown this paper to Professor Lorgeman, who thinks it is worth publishing, but nevertheless I am asking for your opinion. And that opinion never came. So one day he told me what was the difference between the third paper and the second paper. Now in the second paper he had said that if I only assume the emission process to be spontaneous, then the induced part also automatically comes from the formula itself. In the second, since Einstein had objected to it, he changed the position. He said, okay, let's now say that there is only induced emission. Then the spontaneous part comes automatically. You don't have to put it in by hand as Einstein had done. Einstein's idea was that spontaneous emission is an intrinsic property of the atom. Bose had a different idea. He said, no, it's a consequence of the statistics. So apparently one day, Einstein gave him a piece of his mind. He told me, Budo used to talk in a very strong fashion, and he told me, supposing there were only one hydrogen atom in this universe, and it was in an excited state, don't you think it will radiate and come down to the ground state? In other words, spontaneous emission should be there. So Bose said, I was so awestruck by his attitude and so on. He didn't say anything, he came out of the room. But he said, as soon as I went out, the answer flashed in my mind. He said, I should have told him, sir, if there were only one hydrogen atom in the universe and nothing else, then neither you will be there nor I. So let's not talk about such a situation.
I often dropped into Einstein's villa. Any discussion with him was always stimulating.
Sagen Sie nun, wollen Sie wirklich, dass die Engländer ihr Land verlassen?
Of course, we all want to determine our destinies ourselves.
Suppose there was a button in front of you, and all the Englishmen would leave India if you were to press the button. Would you press it?
If God were to grant me such an opportunity, I would not hesitate even for a moment to press it.
Really?
Why do you Jews want to establish a new Israeli state? Even you seem to be fairly inclined in its favor.
I have understood what you're saying. It is an emotional matter and cannot be explained by logic.
2 years in Europe seemed to pass like the blink of an eye. Before I knew it, I was heading back home. But there was a different kind of excitement awaiting me at Dhaka. The excitement of building a modern department of physics at the university.
Bose was very popular there. And, there were very famous Bengalis there, like Professor A.K. Dasgupta, the famous economist, who was a teacher of Amartya Sen, Sukhmay Chakraborty. As you know, Bose had many other interests. He played Esraj, and he also was a great friend of the poet Bishnu De, the great artist Jamini Roy. Bose was like that. He used to interact socially with a lot of people. He was a very popular figure in Dhaka. Bose dabbled into many things. He had interest in chemistry. He had interest in X-ray crystallography. He also, I believe, was the first proponent of the fact that Bokrish or hot spring will emanate helium, both helium-3 and helium-4. And that idea was taken up by Dr. Shyamadas Chatterjee and later on by Dr. Bikas Sinha and the group in the Variable Energy Cyclotron Center. But originally it was S.N. Bose's.
In 1935, while I was still in Dhaka, I wrote a popular article on Einstein for the Bengali magazine Porichoy. 30 বৎসর আগে আইনস্টাইন যে প্রবন্ধে আপেক্ষিকবাদের সূচনা করেন তাহা পদার্থবিজ্ঞানে নূতন যুগের অবতারণা করিয়াছে। জড় জগতে ঘটনাসমূহের বিবৃতির জন্য বৈজ্ঞানিক যে দেশ কাল প্রক্ষেপ ভূমির পরিকল্পনা করেন তাহা দর্শক নিরপেক্ষ নয়। In 1935, Einstein had decided to settle down in New Jersey in USA with a position at the Institute of Advanced Studies at Princeton. Staunch anti-Semitic measures in Germany prevented him from returning to Berlin.
Bose was more of a mathematician. Einstein was more of an observer of nature, a physicist, very intuitive man. Bose was a very good student. He studied in MSc, what at that time was called mixed mathematics, he and Meghnad Saha. He stood first, Saha came second. Einstein was pretty bad in his school studies. Bose is more driven by mathematical logic, while Einstein was governed and driven intensely by phenomena.
Professor Bose never could accept Einstein's criticism of his second paper. Now, he has said this to many of his students, including myself. But since he could not come up with a very satisfactory answer himself, he never published anything. But he told me definitely that I should look at his old papers and see if I can give them any modern interpretation. তুই দেখিস তো বাবা আমার পুরনো পেপার নতুন কথা আছে।
I would say that if you try to find a comparison of that kind of a person in our country who was so intuitive and is a close observer of nature, of phenomena, the only other person I can think of is Rabindranath Tagore.
we were planning to celebrate his centenary, birth centenary, when I was then in S.N. Bose National Center. I was going through various journals and so on at the Indian Association for Cultivation of Science, and I accidentally came across a paper of C.V. Raman and Bhagavantam with the title Experimental Determination of the Photon Spin. I was intrigued. I started looking at it, and then I was amazed because they, right at the beginning, say that this idea was given to them by Bose. And they actually did an experiment to show that Bose was right. In fact, that was the first proper paper in which photon spin was discovered. But in the West, it's been ignored. Now, of course, after I have been saying this, you will see that people have started referring to that paper. So this is how Indians have been, ignored in the past, even a man of Raman's stature.
Bose's works on general relativity. See, there is another letter from Einstein.
In the mid-50s, he suddenly got interested in Einstein's unified field theory. See, Einstein had given his famous general theory of relativity, which was a theory of gravitation. And of course, we have Maxwell's theory of electromagnetism, light. He wanted to have a single theory which will give you both this as well as would explain the quantum phenomena in one stroke. So that was called the unitary field theory. So Einstein was attempting to do that. And in a particular version, he had many ideas to do it. In one of those versions, there was a set of equations. I will not go into the details. It was a set of 64 equations which were all coupled to one another. And it was very, very difficult to solve. At that time, Schrödinger also was interested in the same problem, and he wrote a book called Space-Time Structure, in which he made a comment that most probably these equations have no exact solutions. So we have to somehow try approximations and so on. So one of Professor Bose's students, I don't know exactly whom, who apparently showed that part of the book to Professor Bose. So what I've heard is, well, this was not before my time. So Professor Bose said, oh, Sahib boleche hoy na. The Sahib had said, it can't be done. Okay, leave it with me for some time. And within a very short time, he found exact solutions. So he wrote about 5 papers on various aspects of unified theory. Except one, all were published in French, because he was very good in French. And he was corresponding with Einstein. So Einstein, in one letter, says that it seems you have worked very hard and penetrated deep into the subject. But I have my own ideas. That I think what I have done is the most you can do today. So Bose was preparing to write yet another paper. And this was around 1955, when it would be 50 years of the special theory of relativity. So a special international conference was being convened somewhere in Europe, where Einstein would come, and Bose was also planning to go there. Actually, he did go there. But before the conference, Einstein died. So Bose was, of course, very eager to meet Einstein and talk about his latest paper. So someone went and told him that Einstein had passed away. Apparently, he just froze. And after a while, he took out a copy of the paper, tore it up, and threw it into the waste paper basket. And after that, he never wrote any further paper in physics.
To the teacher who removes all my doubts, wheels my vision into a unity, and thus enables me to gaze on secret knowledge, to that one my homage.
Did you see inside? So most of the letters that Bose wrote to Einstein, he used to address him as a master or sir.
Yes.
Probably he might be the only person who used to address him as a master.
I think they have very unique bond in between them. And it's very hard to find in the history of science such kind of pair like Bose and Einstein.
Bose became famous because Einstein recognized his contribution. And his name got linked to that of Einstein. Here was a man born in pre-independence India. He goes to teach in Dhaka, does a brilliant piece of work. It absolutely shook the world because of Einstein's appreciation of it. But then, at the end of the day, he was also disappointed because Einstein ignored some of his ideas. But that's the way life is.